everyone, this is ECE 4534 Embedded System Design Team 19. For this class, we designed and created a prototype autonomous rover. Each team in the class was required to create an autonomous rover, but the purpose of each was unique. Ours was to simulate a tree remover. It could autonomously detect, purposely mark trees, move to them, and uproot them. For this prototype, we put chopsticks into pots filled with soil and marked them using colors. The main sensor would then check for certain colors, red and yellow, and move to them. The arm mounted on top would then grab the chopstick, pull it out, and store it in an onboard receptacle. The rover would then ideally move to the next tree and continue this loop indefinitely until told to stop. Here you can see us controlling the rover manually. We were sending it commands with specific move and turn amounts. Manual control was very accurate. Our final integration had mixed results. Sometimes the rover would work, and sometimes it wouldn't. We had two modes of control, manual and autonomous. The biggest constant issue was with autonomy, and the rover would always overshoot the pot and would stop further than we wanted, which meant the arm would not grab it at the right place. Controlling the rover manually usually had perfect results for some duration of time, until one of the boards would inevitably fail for some reason or another. All of our components generally communicated properly, however autonomous communications were asynchronous, and there were some issues with communications coming in too fast which would break the system. There were four main parts of the system: the navigation, rover, arm, and server. The server, a Raspberry Pi 3, handled all communications. It used MQTT, a popular connectivity protocol. In using a server, this meant that none of the boards directly talked to each other, but rather through a broker middleman, which could be stored off-site as long as each board was connected to it. Each component had a controller board, which was a TI CC320SF. The board had built-in Wi-Fi, GPIOs, and a slew of other communication interfaces. Here, the rover is acting autonomously. It turns until it finds a marked pot and moves towards it. Then it issues a grab command, which stores the chopstick on board. The rover will then back up and turn until it finds another pot. The next sections will talk about constraints, reliability, robustness of the overall system, and we will have parts about each individual component, where we will elaborate upon the design and functionality of each part in more technical detail. We had multiple constraints for this project required by class specification. We had to use the provided 3-wheel rover, some sort of arm, and everyone must use a TI CC320SF board, which meant one per person. Each board would control a component, and we fulfilled all requirements here. We had to use a Raspberry Pi 3 with MQTT to handle all communications between components. MQTT payloads had to be in JSON format. We fulfilled all requirements here. Our max budget was $400, including the arm costing no more than $75. We spent about $200, including the $50 arm, although we were not most efficient in spending our budget. Of course, any components that we chose had to be compatible with existing software and hardware. An example of an incompatibility would be using an arm that required more than 4 pulse width modulation pins, because the TI boards only had 4 pins that control PWM. So if the arm had, for example, 5 servos that needed to work properly, then it would not work. Another example would be size and power requirements. What would power each component, as using TI boards was not allowed as a power source. Overall, we met all constraints and did not have any issues. On manual control mode, our rover was reliable, except for arm movements. Sometimes the arm would be jerky and stop moving properly, and a reset was required to fix it. This was most likely our design and implementation was not reliable in autonomous mode. Even with ideal conditions, sometimes it would work for many minutes, and sometimes it would fail within a couple. Sometimes it would not even work on start. Depending on our luck, the navigation will either never find a tree and spin in a circle forever, find trees constantly and consistently during a single run, and this was intended, or freeze after finding one tree and properly moving towards it. There were many causes for these issues. Communications were asynchronous on autonomous mode. Each component, which means sensors, rover, and arm, would send messages and store them in queues. Sometimes messages would be sent and queues would fill up if they were too fast. A full queue would cause the rover to completely freeze and stop working, which would require a reset. Messages would also occasionally be sent out of order, and if you go back to the beginning of the autonomous movement clip, you can see the rover backing up before the grab and store is finished. Normally, the physical design also had flaws. The first was that our markers were sloppily made. Secondly, the receptacle is poorly positioned and constructed. This will be discussed in the ARM section. Our design was robust in communications, but not in other areas. We designed our communications specifically so that any missed messages would not have any effect. This was done constantly by sending out state information, rather than just when necessary. The ARM was not robust, but that depended on a number of factors. The tree could not be too deep in the soil, or else the ARM was not strong enough to pull out the tree. If the chopstick was angled, it meant that when it dropped into the receptacle, it would miss and the tree would fall out because of the angling. And lastly, power sources could not be flawed, or else the ARM would jitter and movement would come out of order. For example, the pincers would close and open at the wrong time while the ARM was grabbing. The navigation was robust to an extent. It worked in most environments we tested in: the computer engineering lab, the embedded design lab, and the hallway outside. Each environment had different lighting and flooring. Other groups that we noticed were not quite as robust, and their cameras failed when in those different environments, and they had to recalibrate every time. However, on the flip side, sometimes marked trees would not properly be detected if the marker was made sloppily, because usually the shape would be distorted and the camera would not sense it properly. The rover was robust. It worked with very reasonable accuracy on tile and on the strange rubbery mix in the embedded lab without need for adjustment. Navigation was the heart of our system. It determined where the rover needed to move, when it needed to move, and when to grab. The ARM and rover had no communication or knowledge of each other, and all information was passed through navigation. There are two sensors on the rover used for this: a Pixie 2 cam, which is off the shelf, and the IR sensor, which is also off the shelf. The Pixie cam was used for sensing marked trees, which it looked for colors, in this case red and yellow. Ideally, it would sense other colors to avoid, but this was not implemented in time. The infrared sensor was used for short distance sensing, between 6 and 15 centimeters. The Pixie cam was not accurate in that range. The infrared sensor took priority. Once the rover got close enough, it would rely on the IR sensor to close into the proper distance to reach and grab the tree. In every component, there are tasks and queues. Tasks are individual threads that deal with specific issues and write messages to queues that other tasks can read from for information. Tasks run in parallel, so for example, each sensor had its own task, and both could read from the same time, although this was quite unnecessary. Navigation had 5 tasks with corresponding queues. The first task dealt with communications up and down, so if the ARM or rover sent information, or the nav had to send information to the ARM or rover, this is where it was done. The second and third tasks dealt with passing messages to the appropriate locations if necessary, be it a move or a grab. The fourth task read from Pixie Cam using an I2C bus and parsed the output. The fifth and last task read the IR sensor using analog to digital and parsed the outputs. The rover is a 3-year-old custom design for this class. Every group got the same rover. It is capable of 360-degree movement and is quite heavy duty. It uses serial peripheral interface bus, called SPI, to communicate with motor encoders. It uses proportional integral derivative control loops, called PID loops, to properly drive the motors as per class specification. This loop continuously calculates error between desired and real value and adjusts for this. The rover responds to commands to move, set in centimeters, and to turn, set in radians. There were 3 tasks. The first task was for communications to and from the navigation. The second task was a state task to figure out move commands. The last task was a PID controller to control the PWM, pulse width modulation, and SPI. The ARM was an off-the-shelf model from Microbot Labs, model ARMUNO 2.0. It had 4 servos for different movement: pincer, horizontal, vertical, and rotation. Each servo was fed 5 volts from an onboard portable battery pack and controlled using pulse width modulation. It read commands from the MQTT server, and when it detected a grab command specifically from navigation, it would initiate operation. The rotation pin on the control board was not working, which forced us to put storage receptacle on the front of the rover instead on the side. This led to reliability issues that I mentioned earlier. One feature not implemented at the time was variable distance grabbing. The controller parses the distance passed to it from the iris sensor, but I never used it properly. The ARM had 3 tasks: communications to and from navigation, the state task to make the ARM move, and servo tasks to control each individual servo separately using PWMs. The ARM had no knowledge of the rover. In conclusion, we had envisioned a project at the beginning of the semester that was not overly ambitious, but we regret not getting more done. However, we are satisfied with what we have working, which is a sometimes working integration. It is very satisfying to see it all come together in a tangible product, which is unlike some other classes that we have taken in the past. Our implementation was not reliable or robust as we would have liked, and we did not get obstacle detection working, which would not have been particularly difficult but very useful. This prototype design could have been extrapolated to any sort of rover grabbing type operation in a controlled environment, maybe something like tree planting or serving in a restaurant or at a party. The opportunities are endless, and seeing this go further would have been great. Alright, thanks for watching. This is Team 19 for Embedded Systems Design, Fall 2019. Goodbye.